Okay, the next topic in Caligula property deals with two properties, in fact. How we change boiling point, freezing point when we add solute to a solvent. How does that affect the physical properties of the solvent in terms of boiling point and freezing point? Now, to get a good idea of what's going to happen here, it's going to affect the boiling point because what will happen, just like we talked about vapor pressure, the solvent is going to bond to the solute, which is going to make it difficult to boil off, or they have to find a way to break apart from the solute. And the only way we can do that is by increasing the temperature. Now, the boiling point is defined as the temperature which the atmospheric pressure is the same as the vapor pressure. Well, we just found out in Raoult's law that the vapor pressure drops when you add a solute, when the temperature is not changed. So that means the amount of heat that's going to have to get added to push it up to the atmospheric pressure, now that it's dropped, is going to be a higher temperature. So the temperature of increase is going to be proportional to the concentration of the solute that's been added in moles per kilogram, or molality. The freezing point is going to have the same issue. The freezing point, however, is not going to increase in freezing point. It's going to decrease in freezing point because at 0 degrees, water wants to assimilate itself in such a way where crystals are formed in a pattern that is amenable to what water needs to have enough space to pull apart and create the crystals for that. Well, if it's attached to something else, it's going to take longer for it to adjust itself. And so as the temperature decreases, it's still not going to work until all those water molecules with their attached solute is going to align itself in the way that it needs to do. So the temperature will actually drop. So the freezing point drops while the boiling point increases when you add solute. Now this is why we add sodium chloride crystals to the road when it snows or ices. And the reason for that is you throw it on there. Now that doesn't mean anything's going to happen, but a car is going to run over it. And the friction between the tires and the ice and the salt is going to create heat. Any friction creates heat. That heat will then melt the water, and the water then will dissolve the crystals, and now you've got a solution in which the freezing point is lower than what it was before. If you throw enough salt crystals on there, it's going to turn that into slush and eventually water. Or not water, but it'll be water with salt dissolved in it. So you have a saline solution that you're creating there. So that's how all that works. That's why we throw salt crystals on. And of course the problem with that is that salt will allow what we call an oxidation process between the water and the iron of the car, particularly if the car has any dinks or anything with it, which will expose the iron or steel to the conditions outside. That's when the rust will occur. So generally, if you want to buy a car, a used car that's not going to have much body damage, you want to go to an area where it's warm but not near an ocean, because there's lots of salt in the atmosphere for those areas. So go to mid-Alabama or mid-Mississippi or Texas. Texas has wonderful, because it's not very humid there most of the time, although it's hot enough. So that's what we're looking at. It's the mathematical relationship. And this all describes what I was just telling you about here. So let's take a look at a scenario here. Now, first of all, there's a chart on page 528 that you should be familiar with. It's at the bottom part of the page. It lists various solvents, it gives their freezing point and their KBs and KFs. Now, we'll talk about KB and KF in just a little bit here. The KB is what we call a boiling point elevation constant. Like I said, when you add a solute to water, the boiling point is going to increase, and that rate of increase is a constant called K sub B. And if you multiply that K sub B times the molality of the solution, you're going to get, and add that to your original boiling point, you're going to get a new boiling point. So because it's increasing, we're going to put a plus sign there to show that that's going to add to it. Freezing point, however, has a Kf value that we call a freezing point depression constant, or Kf. And the Kf is going to be multiplied by the molality as well, but the difference here is that you're going to have a subtraction sign between the original freezing point and the product of the molality and the Kf. Now these two Ks, the Kb and Kf, the label for their constants is degrees Celsius per mole per kilogram. And you can see, if you have moles per kilogram for M here and degrees Celsius per mole per kilogram here, the moles per kilogram are going to cancel out, leave you degrees Celsius, and you're going to take your freezing point and subtract that product of those two in degrees Celsius. So let's take the example. Now, I'm using the same scenario as what we used last time, in which we take 50 grams of sodium chloride and adding it to 100 grams of water. Now, the only issue I have with this example I'm giving, I'm just trying to be consistent with the other, is that there's something called an I factor here, where you're actually going to double the molality. We're not going to do that just yet, that comes later. We're going to assume that the I value for this is 1. And if you don't remember the I value from Chem 1, don't worry about it, we'll discuss it again later on, but it's called the Van 't Hoff constant. But we're going to pretend like it's a 1 and not worry about the products of this. Anyway, it says, what would be the freezing point and boiling point of the solution if you have 50 grams dissolved in 100 grams of water? Okay, so we have 50 grams of water again. I'm sorry, 50 grams of sodium chloride. And we said it was 0.855 moles of that. We have 100 grams of water. Now, we don't want to change this to moles because molality is moles per kilogram of solvent. The solvent here is water. Now, again, I emphasize, not every time is water going to be the solvent. I think one of your problems has something else. So that chart on page 528 will be very important in finding original freezing points and boiling points and their Kf and Kb values. Kb and Kf values are inherent only to the particular substance you're looking at, so don't use it for other solvents. Anyway, we have to change this to kilograms, so it's going to be 1 kilogram over 1,000 grams, and that's going to give us 0.100 kilograms. So the molality of the solution is going to be 0.855 moles divided by 0.100 kilograms, and this is going to give us 8.55 moles per kilogram, or little m. Molality. It's a molality solution. Molality. All right. So, how does that affect the freezing point and the boiling point? Well, let's do boiling point first. Boiling point is defined as the original boiling point plus the molality times Kb. And B for boiling, so that tells us we're using the right constant there. So be careful of that too. Don't use the Kf for the Kb. We know the original boiling point of water is 100 degrees Celsius. The molality here is 8.55 moles per kilogram times, and the Kb, if you go to the chart on page 512, or 528 rather, the Kb for that is 0.512 degrees Celsius per mole per kilogram. So this is your formula you're going to have set up for that. Let's cheat a little bit, take a look at the answer here. There we go. And that's freezing point. There's boiling point right there. So 512,867, and we get 104.44 degrees Celsius, or round out to 3 sig figs, 104 degrees Celsius. Let's do the freezing point now. It's pretty much the same thing, except you have a Kf instead of Kb, and you're going to change that plus sign to a minus sign. So Fp equals the original freezing point minus your molality times Kf. So this, we know the freezing point of water is 0 degrees Celsius minus 8.55 moles per kilogram of solution times 1.8. Oh, the numbers are failing me today. Let's cheat again. Let's see what that is. 1.858. Hello. 58 degrees Celsius. And then we go check out the answer to that. I remember some in the neighborhood of 14 below zero. Let's check it out. And, oh, it's not even close, 16. So it's negative 16.1 degrees Celsius run off the 3-sig phase. So, those are your two values. It's a very simple process. Just be careful you know what the solvent is when it's not water. And yes, you'll be allowed to use a chart when we have the quiz on this stuff. So, practice problems, 548, 61 through 64, all of them. And good luck.